Alright, here we have another flagpole problem. What we want to do is we want to find the magnitude of the resultant force. Notice we have two forces shown here. We have a 560 Newton force as well as the 700 Newton force. So we're going to find the resultant of that and then do the magnitude. And then we're also going to find the direction angles of that resultant force. So remember the direction angles, we have alpha, beta, and gamma. So let's go through and do that. First, let's go ahead and write down our coordinates of these points that are shown. If we look at point B, which is over here, our coordinate for that would be 2, -3, and 0. Our coordinate for C is going to be 3, 2, and 0. And then finally A, which is at the top of the flagpole, would be 0, 0, and 6. Now, to find the resultant vector, we need to be able to add vectors. So we're given the magnitude of these forces in the cables. We need to get the vector forces. Oops. So let's do that first. Let's start with a 700 Newton force. So our force for that one, let's just call that F1, will be the magnitude times the unit vector of the line going from A to B. Alright. So now notice we're going from A to B, so that's going to be important when we're calculating our unit vector. So remember the terminal point comes first, and then we subtract off the initial point. So here we're going to have 2 minus 0 I plus -3 minus 2j, and then plus 0 minus 6k. And then we put that over the magnitude. So the magnitude of that line would be the square root of 2 squared plus 5 squared plus 6 squared. Alright, and then that's going to give us our F1. So I'll just write it in bracket format. So our x component is 173.65, and then we have -434.12 for y, and then our z component is going to be -520.95, and that's in newtons. Now let's do the same thing for the other force. Let's call it F2. We're going to have our magnitude times the unit vector for the line going from A to C. So now we'll have 560, and then we'll multiply by the unit vector. So again, we're going towards C, so we're going to have the coordinates of C minus the coordinates of A. So if we do that, we have 3 minus 0I plus 2 minus 0j, and then plus 0 minus 6k. And then put that over the magnitude, which will be the square root of 3 squared plus 2 squared plus 6 squared. Alright. So now, multiplying all that out, you end up with 240 for x, 160 for y, and then your z component of that force is a -480. And that is in newtons. Now for our resultant force, we want to sum up the forces present, so we're going to have F1 plus F2. Remember, when you add vectors, you add the like terms. So we're going to add the two I components together, which gives us 173.65 plus 240. For the y direction, we'll have -434.12 plus 160. And then for the z direction, we're going to have -520.95 minus 480. Okay, so do that addition there, and we end up with 413.65 and -274.12, and then -1000.9. That's newtons. So that gives us our resultant force that's created by those two forces in the cables. So you can see from that that overall you have a positive x component of that force, and then the y and z directions are both going in the negative direction. So it's going downward and then over towards the left. Now if we want the magnitude of this, which is what we were asked for, we'll just do the square root of the sum of the squares. So we have the square root of 413.65 squared, and then plus 274.12 squared, and then plus 1000.9 squared. And that gives us 1117.21. So that's the magnitude of the resultant force. Next we want to find alpha, beta, and gamma. Alright. Now remember, we can find those angles by using the unit vector. And we want those angles for the resultant force, so we're going to use the unit vector of the resultant force. So the unit vector is going to be the resultant force vector over the magnitude of the resultant. And we just found both of those, so if we write those out, we get 413.65I minus 274.12J minus 1000.9K, and then we're going to put that over the magnitude we just found, which was 1117.21. That gives us the unit vector 0.37 for x, negative 0.245 for y, and negative 0.895 for j. Okay. So you can, for k I mean. So you can see our k component has a much bigger component than the other two. Now we'll use these three components here to get alpha, beta, and gamma. Remember, alpha is going to be the angle that we can find from the x component, because alpha is the angle between the positive x-axis and the force. So we can say that cosine alpha is 0.37, where the 0.37 is from here. And then you do the arc cosine of 0.37 and you'll end up getting 68.28. Alright, and then we do a similar thing for the other two angles. Cosine beta, that's going to be equal to your y component of the unit vector, so negative 0.245. Do the arc cosine, you get that beta is 104.18 degrees. And then finally cosine gamma is going to be negative 0.895. And we do the arc cosine, you get 153.51 degrees. Alright, so there are our angles. Now remember, these are the angles between the positive axes and the force. Alright, so our force is going in the positive x and the negative y and the negative z direction. So if we say that this was the top of that flagpole, we're going to have the resultant force going down like this. Now if we attach the axes to this, we could draw the angles. Let's switch to a different color here. Alright, so if we did that, this is still our x, this is still y, it didn't switch colors. This is x, this is y, this is z, so then you could draw these angles. So right here would be our alpha, and right here would be our beta. Notice it's greater than 90. And then our gamma would be right here. Okay? Label data. So that's kind of how we use the cosine direction angles and how we find them using the unit vector.